I've only partially planned out this video, so let's kind of wing it. What I want to do, I'm teaching electrodynamics. We're using this textbook. And I want to go over the first 4 chapters as a group because they're all related. And then once you get into chapter 5, we get into magnetic fields. So the name of the book is Electrodynamics, but we're in electrostatics, right? Because we haven't looked at moving charges yet. So, and I put these here because this is the key. They're really about electric charge, electric potential, electric field. These are the most fundamental things we have in these 4 chapters. How do we represent these and how are they all related? Ready? Let's go. Okay, I got my notes. Let me look at my notes here. Okay, the first thing is just your basic, how do we calculate the electric field due to a point charge? Let me also say, there's a bunch of stuff in these 4 chapters. I'm not going to go over everything. I don't cover everything because it's too much. So if you're looking for a particular topic that I didn't cover, I may have a video about it, but maybe I didn't cover it at all. Oh, okay, that's enough. So imagine that we have, and I'm going to do this the way I do it, not the way the book does it. Suppose I have a charge there. I'm going to call this RQ, the vector location of that charge, and then I have a point over here, RO, the vector location of where I want to find that electric field. Well, the first thing you need to do is to find R. So R is going to be RO minus RQ. And then I can find the electric field. It looks like this. E is 1 over 4 pi epsilon naught Q over the magnitude of R squared R hat. So R hat is a unit vector in that direction. There's another version of this that's sometimes useful. 1 over 4 pi epsilon naught Q over the magnitude of R cubed times R. We can use this in a lot of different situations, and we will. Now, imagine that I have more than one point charge. Well, if I have multiple point charges, I could say the electric field, I feel like my board's a little crooked. No, I just wrote crooked. The electric field is 1 over 4 pi epsilon naught, the sum over I of Qi Ri hat over Ri squared. So basically this just says if you have more than one point charge, the electric field is the vector sum of the individual electric fields. Got that? Okay, now what if I have a charge distribution that's not points? What if I have a charge density? Well, then I can calculate the electric field as 1 over 4 pi epsilon naught. I don't like that. E is 1 over 4 pi epsilon naught, the integral over the volume of rho r hat over r squared dv. So that's a volume integral. The book uses d tau for volume elements. I don't like that. I like dv. I understand, hey, we use dv for change in potential, so that's a problem. Just don't make it a problem. It's easy. Okay, now there is another way to find the electric field, and that's using Gauss's law. So Gauss's law says that, I'm going to write it out first. It says the electric flux E dot, that's a vector, dot n hat dA over some closed surface. So this is a surface integral because it's dA is the area element over a closed surface. It has to be completely enclosing some surface. So it can't be a sheet of paper. It has to be a ball or a box. And that's going to be equal to Qn over epsilon naught. So this says that if you take some shape, and it doesn't matter if it's useful or not. Let's just say I have this shape, it's a like that, and I have a charge right there, and I calculate the flux, no, that'd be this way, over this, right? Those are my electric fields, and then I have to take E dot n hat at all these places, add up E dot n hat dA, and I'd get the total charge inside. Now that would work, but not be useful. So what we do is we pick surfaces that match the shape of the field. Suppose I have a point charge, the easiest case. If I assume a radial electric field so that E is equal to E of r hat. So it depends on the distance away and it's in the r hat direction. I can choose to integrate over a sphere and the integral becomes very easy. So we can use that to get an expression for the electric field. But you have to make, if you want to use Gauss's law to find the electric field, you have to know something about the electric field first. Okay, that's Gauss's law. Now, according to the divergence theorem, the divergence theorem says that some vector A dot n hat dA is equal to, what did I write it down as? Yeah, it's del. This is equal to the volume integral of del dot A dV. Yeah, dV, because that's a scalar, dV. That's a volume integral. So if I integrate over the surface area of some vector, any vector A, then I could also integrate over the divergence of that over the volume enclosed in that. Well, this is equal to, this is equal to Qn over epsilon naught, but I can write that as 1 over epsilon naught times the integral of the volume rho dV, right? So rho is the charge density. So that means that this thing has to be equal to that thing, and we get the differential form of Gauss's law for electric fields. Oh, if I change this to E, del dot E is rho over epsilon naught. So that's the same thing as that. That's the differential form. This depends on some finite volume. That does not. Moving right along, turning the page on my notes. Okay, next we have the definition of electric potential. So we define the change in electric potential as negative the integral from A to B, point A to point B, of E dot dl. That's how we define the change of potential between 2 points, if you know the electric field. Now, if we have a point charge, then if we put in the electric field due to a point charge, then we get delta V is negative 1 over 4 pi epsilon naught, the integral from r equals A to B of Q over r squared dr, and that's going to be 1 over 4 pi epsilon naught Q over r A to B. Now the point here is that if I integrate a closed path, so delta V equals negative the integral of a closed path of E dot dl, well, if I use that for a point charge and everything is a point charge, right, with a sum of point charges, then I'm going to get A to A. So imagine I'm going like here, A, and back there. So my starting and ending points are A and A. So I get 1 over A minus 1 over A, 0. So this is an important thing for electric fields, that, which is not always true, we're going to find out later. It's a conservative field, E dot dl around a closed path is equal to 0. We can use this along with Stokes' theorem. So Stokes' theorem says that the integral around a closed path of A dot dl is equal to, looking it up because I forgot already, del cross A dot n hat dA over a surface. So if E dot dl is equal to 0, then the integral of del cross E dot n hat dA is equal to 0. So that means that the curl of E with del cross E is 0. And that's important for some other stuff later. Now, what if I have a charge distribution rho? How do I find the potential? So the first thing is, instead of finding a change in potential between 2 points, we pick one of the points as infinity. So we find the potential with respect to infinity, and we set the potential at infinity to be 0. So with that, I can find the potential of any charge distribution as negative 1 over 4 pi epsilon naught, the integral over the volume, rho dv over r, because that's the potential due to a point charge is 1 over 4 pi epsilon naught r, and then I have rho dv as the charge. That's an important equation. If we use, so what if I want to go backwards? I know that delta v is negative the integral of E dot dl. Well, what if I undo that? Then I can see that E is the divergence, negative the divergence of the potential. And now, if I use that along with Gauss's law, so remember Gauss's law is the divergence of E is rho over epsilon naught. If I put this in for E, I get the Laplacian of the potential is negative rho over epsilon naught. Yep, that's important too. Okay, so we have these 6 equations now. Let's see if I can write them down from memory. So the first is this one, E 1 over 4 pi epsilon naught, the integral of rho dv r hat over r squared. That's the finding the electric field if I know the charge density. Well, how do I find the electric field if I know the electric potential? That would be this. E is negative the gradient of the potential. Okay, what's the equation for the potential? Well, V is 1 over 4 pi epsilon naught, the integral of rho dv over r. That's if I know the charge distribution. But what if I know the electric field? Well, then V is going to be equal to a negative the integral of E dot dl. So I have 2 equations to find the electric field, one using charge density, one using the potential. 2 equations to find the potential, one using charge density, one using electric field. Well, I should have 2 equations for for the charge density. So the charge density from the electric field, well, I know this, negative rho over epsilon naught is the Laplacian of the potential. I also know that del dot E is negative, no, not negative, it's rho over epsilon naught. So those are the 2 ways to find the charge density. So charge density from potential, charge density from electric field. That's chapter 3. There is some other stuff in there about conductors, but I don't think they're super important. I'm trying to hit the highlights. Okay. You know, this is, if you're still here, hello, if you're still here, welcome. This is part of my playlist for this course. I'll put a link to the whole playlist down in the description so you can see all the different videos if you want, and maybe you like them. I don't know. Okay, next we're in, there is a section on solving boundary value problems for the potential, basically solving this problem if there's no potential. The Laplacian of V is equal to 0. There's a bunch of great stuff in there, okay? There's solving it by separating variables for a 2-dimensional case. The 1-dimensional case is really great too. I don't want to do, if I describe that, I'm just going to have to do the problem. I have a video on that. I really enjoy solving this numerically for 2-dimensional boundary value problems. It's pretty cool, but again, I have videos on that, so I don't want to go over that. The next big thing is the dipole. So suppose I have 2 charges, a plus q and a minus q, on the z-axis like this, and I want to find the electric potential and the electric field everywhere. Well, I could just sum up the charges, right? The electric fields do the 2 charges. That still works. But if I am far away, or the distance between them is very small, then I can use some approximations. So we first define what we call the dipole moment, P, as the sum over I, Qi, Ri. So in this case, you know, if these are separated by a distance d, then the dipole moment would be Qd, right? So it has no net charge. this dipole. You have a positive and a negative, but it still makes an electric field. That is important. There is this whole, how do we approximate the potential due to this dipole? So imagine that we switch this to spherical coordinates. This is the angle theta. This is the distance r. So I'm not going to derive it. Okay, I've already done that. So V is equal to, I even forgot this one. The potential is P cosine theta over 4 pi epsilon naught r squared. Yep, got it. Okay, so P is that dipole moment for this particular case. Theta is the angle between the dipole axis and where you want to find that charge. Now, it doesn't matter where the phi value here, right? That's constant, and that gives you the electric potential. Now, if you use spherical coordinates to take the gradient of this, well, you can find the electric field because E is negative del V. But you have to use the del operator in spherical coordinates. If you forget the del operator in spherical coordinates, that's not a problem because everybody forgets the del operator in spherical coordinates. But look, it's in the front of the book, okay? So you can look it up. We all forget. It's nasty, a little bit. But if you do that, you get the following. You get the electric field in spherical coordinates is looking up P, is there a P? Yeah. P over 4 pi epsilon naught r cubed times 2 cosine theta r hat plus sine theta theta hat. So it tells you the direction here. So in this case, theta hat is this way, r hat is that way. Okay, so you have a vector, and then the phi coordinate doesn't really matter. Now, there's another form that I like, the Cartesian coordinate form or the generic coordinate form of the electric field due to a point dipole moment. E is 3 times P dot r hat minus P all over 4 pi epsilon naught r cubed. So this one, if you're doing things numerically, which I like to do, then this is the expression that works because you can use P r hat in Cartesian coordinates. You can do the dot product. You can find the electric field. Bada bing. No problem. Okay. Moving on. Now, it turns out that any charge distribution you can represent as a dipole moment plus a total charge plus a quadrupole moment plus a octupole moment and all that thing. I didn't go over that. But the dipole moment's important because when we talk about insulating material, dielectrics, we have an induced polarization, and we represent that with dipole moments. So the dipole moment's super important to me. I don't think you use the quadrupole moment that much. It's not as important. Okay, so now we're into materials. So if you have an insulator, and you apply an electric field, the insulating material in there becomes polarized. So in this case, we'd have these little plus minus. I don't feel like I'm going to draw all these. Let's just draw 6. Keep getting it backwards, like that. So each one of those dipole moments, we can say the dipole moment is some constant times the electric field. This is true for a linear polarized material. Alpha is the polarizability. It's just a constant. Okay. It says that the greater the electric field that you apply to that, the more those move apart and the greater the dipole moment. Now, this is linear, meaning that the dipole moment is in the same direction as the applied electric field. Oh, I dropped my chalk. Good thing it didn't break. It doesn't always have to be that way. You can actually apply electric field and get dipole moments in different directions, but we're not going to deal with that. The other thing that we need to think about is to say, okay, this electric field applied makes a dipole moment. Those dipole moments now make new electric fields. But we're going to assume that this dipole moment doesn't influence that dipole moment. Okay, they're only just influenced by that. So that's not necessarily true, but it's good enough. If these make really, really, really tiny dipole moments, very small dipole moments, then the impact on this neighbor is not going to be that big. But it is there. Okay. So. Another thing so the dipole moment P depends on the electric field. We do have this other value called P, it's capital P, and it's the dipole moment per volume. And this is called the polarization. And it's a way to describe the bulk properties of the whole thing instead of looking at individual dipole moments. Okay? But just so you know that if you do have the polarization, you could find the dipole moment of the whole thing as the integral of P dV. Right? You could integrate over the volume to find that. But we're going to use the polarization in our calculations. Okay, I'm not going to derive this, but we do have two very important properties when we talk about the polarization of some object. So imagine that I have, I just erased it. Okay, I'm going to draw them as arrows. So these are my dipole moments in this object. Well, this is the negative side and the plus side. So what's going to happen is I'm going to have an effective excess charge, unpaired charges on that side, unpaired charges on these side. So this is going to what we call bound surface charge density. So we're going to really say that we have two types of charges. We have free charges, just extra charges that are laying around, and then these charge separations caused by induced polarization. That's the key. A bound charge is on a neutral object, but caused by polarization. We can calculate the value of the surface charge density sigma. Sigma b is just going to be the polarization dot n hat. So here you can see that if I had up here, n hat is a vector perpendicular to the surface. So since it's perpendicular to the polarization, there's no charge buildup there, right? But here, P and n hat are in the same direction, get a positive direction. Here, P and n hat are in opposite directions, I get a negative charge density. So this is how we calculate the charge density due to a polarized object. What if I have something like this? Here's my polarization vector in some material. Yes, I will get a charge density on the surface. But if you drew this as actual charges, it looks like this. So here's one, here's one, here's one, here's one, here's one. Now I have these unpaired negative charges on the inside. This would be a positive divergence of the field. Remember this, zero divergence. This is a positive divergence. So this has a positive divergence, and that results in a negative charge density. So we have bound charge density is negative the divergence of the polarization vector. Those are both really important, right? Because we're going to have two ways to think about the electric field due to polarized materials. One thing that we can do for the polarization is say the polarization is epsilon naught times this chi susceptibility of the electric field. It's a lot like that E alpha, but this is the polarization and not the dipole moment. Okay. Now we get to the displacement field. So this one's not too hard to derive, so I'll just do it real quickly because it'll help us. So remember, this is Gauss's law. Del dot E equals rho over epsilon naught. But what if I separate the charge density into bound and free? Then I can write this as rho b plus rho free over epsilon naught. Now I can multiply both sides by epsilon naught, and I get del dot epsilon E equals rho bound plus rho free. Now, using what we just said about the polarization, I have del dot epsilon naught E is going to be, the bound charge is negative del dot P plus rho free. If I move that to the other side, I get the following. Del dot epsilon naught E plus P equals rho free. And we define D as epsilon naught E plus P. So in that case, Gauss's law says del dot D is rho free. Kind of a big deal, right? So here I'm defining a new term called the displacement field, the electric displacement field. And in that, Gauss's law only deals with the free charges. Now, the bound charges still matter, but they're in that P thing right there, okay? So this is just the free charges, and there's no epsilon naught because of the way I divided it out. You could also write this, D dot n hat dA equals Q free in. I call it Q fin. That's the same thing. This is Gauss's law. It just looks different because we wrote it in terms of the displacement field instead of the electric field. This is Gauss's law. It looks different. Okay. So I just want to point out a quick, I'm not going to calculate anything, but suppose I have a positive charge surrounded by a dielectric. So what's going to happen is that this positive charge is going to make an electric field in here, and it's going to create a polarization like this. That polarization is then going to make a surface charge density over here. And you can see that in this situation, since it has a divergence of the field, it would also cause a bound charge density. So I'm going to get sigma B, rho B. Now, if I want to find the electric field anywhere, I could use Gauss's law, E dot n hat dA equals Qn over epsilon naught. And so to do this, what I would have to do is first calculate the surface charge, calculate the charge density, calculate the other surface charge, and I could do it. Or I could use the other version. D dot n hat dA is Q free in. And in this case, it doesn't matter about those bound charges. I just ignore them. And I get the displacement field is the same everywhere. But then if I want to go back and find the electric field, I would say, okay, now D is epsilon naught E plus P, and then I could use that to find the electric field. Okay, I'm not going to do that problem. Now, here we have one other thing that I need to mention. If we use the susceptibility here, this is epsilon naught E plus epsilon naught chi E, then I can write this as epsilon naught 1 plus chi E, and we call that epsilon E. Okay, so it's just a different constants, different ways to describe the dielectric constant. It's not a big deal. And that's that for the chapters really 1 through 4. 1 was all about vectors and stuff like that. Important stuff. But 2, 3, 4 were about charges, electric field, and electric potential. And that's your summary. Now, in the next stuff, we're going to get into magnetic fields so we can start over and do more awesome stuff. Hope that helps. Talk to you later. Playlist down below if you're still here. If you're not still here, then I hope you have a great day. I'll talk to you later.